Hello, everyone. I want to welcome you to the first of our online lectures. If you can try to think back to before all of this happened and before we had spring break, what we left off with discussing was chapter 8, where we were getting into the idea of space explorations. Of course, what we had talked about was mainly with regard to telescopes and how you can use telescopes to tell something about stars and objects out in the night sky. And one of the last things we discussed was the Doppler effect. And this was a way of telling whether or not the light from an object indicated that the object is actually moving. Because just like the Doppler effect that we're used to with sound, light can also have this effect in which the motion towards or away from us will shift the frequency of the light. This isn't necessarily perceptible in the shade of color that you see. However, it is something that's detectable if we look at the spectrum of, for example, a star or a galaxy, and we know very well, it's well constrained what a line should be at in terms of its frequency if it is standing still. And so if we see that same set of lines that indicate something like hydrogen and it's shifted towards the red or blue end of the spectrum, that means that it must be moving towards or away from us. And we discussed how to tell the difference between those two, the red shift meaning that the object is moving away from us, the blue shift meaning that the object is moving towards us. This is an effect that can be used to detect things that are not seen, such as planets orbiting other stars. And so what happens in this case is that the light from the star, you can't see the planet itself because it's not giving off visible light of its own. However, buried within the spectrum of the star is a way of detecting the presence of the planet. So when we receive the light from the star on Earth, we may notice that at some points in time, the spectrum indicates lines at the frequency we would expect if the star were not moving. And then later on, perhaps those lines are now redshifted, indicating that the star is moving away from us. And then later on again, they're back to the usual position. And after that, we notice that they are now blue shifted. So what could explain this pattern of regular unshifted lines followed by red shifted lines, followed by unshifted lines, followed by blue shifted lines, and having that repeat again and again in a periodic manner? This indicates that the star is somehow moving alternately towards us and then away from us. What could be causing it to do that? The implication is that there's some unseen object that is, through the force of gravity, pulling on the star and causing it to wobble slightly towards us and away from us. Now, this cartoon is exaggerated just so that you can kind of see that motion unfolding. The amount that you see these lines shift by will indicate something about the mass of the thing that is pulling on it gravitationally. The more massive something is, the more you will see a shift there. There's also some unknown factor that has to do with whether or how we're looking at the system to our line of sight, and that can confuse the matter. But suffice to say that for a planet, you're going to only observe a very small shift, but it is detectable. And it's something that has been used to infer the presence of planets orbiting other stars for the past 25 years since the discovery of the first exoplanet in 1995, which was discovered in this manner. The method was then coined to be called the radial velocity method. Now, this isn't the only way in which you can detect extrasolar planets. There are other indirect detection techniques, one of which relies upon the looking for the dimming of the starlight as the planet crosses in front of the star to our line of sight. Now, you can imagine this is not going to happen for all planet systems. If we are looking at a star orbiting a star like this and a planet orbiting around it like this so that it's face on, then the planet will never cross in front of the star to our line of sight. But as long as it's inclined to some sort of appreciable angle, there's a chance that it could actually eclipse the star, or what we call transit the star, and dim some of the starlight. The amount of dimming, so that would be this kind of orientation that you see in this cartoon here instead of what I've just drawn here. The amount of dimming is very small. It's something that you might expect. The comparison is like looking for the dimming of a giant spotlight due to a bug flying across it. And so it's very small indeed. You're looking for 1% drop or less in the brightness. But again, it is something that is detectable. It's something that has been a method that has been used from the ground with telescopes to infer the presence of extrasolar planets. And it's also been used by space telescopes. Last time we talked about different space telescopes. The Kepler mission in particular, which was launched in 2009, has discovered a number of planets, many planets, thousands of planets actually, outside of our solar system by using this transit method. And of course, since not all planet systems will be aligned in such a way that we will see a transit occur, the number of planets that Kepler has discovered only represents a small portion of all the extrasolar planets in the direction that it is pointing towards. It's always staring at one patch of the sky, actually. Nevertheless, it amounts to a lot of new discoveries. Here is a graph as of about 5 years ago of the planets that Kepler has found. What's interesting on this graph is that now that we know of thousands of planets, we can now talk a little bit about what is typical in terms of planets outside of our solar system. So from this graph, you can see that a typical extrasolar planet or exoplanet is going to be probably larger than the Earth's size. We can see here where it says 1, that is the size of the Earth, right here. And that most of these planets that have been discovered are larger than that. So probably if I had to guess at, say, the average size of a planet based on this population you see here, maybe it would be around here, right? Around two times maybe the size of the Earth. You can also likewise look at the x-axis and figure something out about what the typical orbital period is. So what is a year on a typical exoplanet? For us, it's 365 days. So, for us, that would be somewhere around here, right? But that's rather long compared to most of the planets that you see here. Perhaps an average orbital period, if I were to just take a stab at it based on the data points you see here, might be something like 10 days. So in only 10 days, a planet that's twice the size of the Earth orbits its star. That's more like a typical planet as far as what we can tell. So what that implies is that these kind of planets, these larger planets, must actually orbit closer to their stars than the Earth does, and many of the planets in our solar system do, in order to whip around its star at such a high rate of speed that it's completed a year in only 10 days. So that's interesting to note that we aren't necessarily typical here in our solar system. When this field was beginning to, when discoveries were beginning to be made and people speculated about what planets would be like around other stars, we assumed that it ought to be similar to our solar system. And that assumption is showing through the data not to necessarily be true. Okay, so that basically wraps up the discussion I wanted to have about space telescopes. I want to move on and discuss a few different types of probes in our continuing discussion of space exploration. So those would be flyby probes, orbital probes, and lander probes. And we'll take a look at an example of each one of these. So for a flyby mission, what you're doing is, as the name implies, flying past a planet or other solar system body, and then you're moving on. You're not really orbiting, or you're not really lingering. You're just moving on. The reason you'd want to do this is if you want to get some closer up data than what you could get from the ground, and not yet commit to necessarily a targeted mission where you have an orbiter or lander to that solar system body. But it'll give you some initial reconnaissance, initial images, and help you lay the groundwork for potential future exploration. So, an example of a flyby mission is the New Horizons, which was launched in 2006 to the outer solar system. And you can see that it has gone from, obviously, this is a little out of date. It's been longer than 10 years now, since 2006. But it's gone quite far indeed. It's gone beyond Jupiter, beyond Pluto, and its moon Charon. It took a nice close up of that, which we'll talk about in a minute. And it is now somewhere out in the Kuiper Belt where all of those other Kuiper Belt objects are located. So you can see the timeline of where it was at what point in time. When it reached Pluto and its moon Charon, it was able to take some images, learn about the orbit of Charon around Pluto, and also take some high resolution images and sent those back to Earth of Pluto and its moon Charon. Okay, next I want to talk about orbiter probes. These are, again, as the name implies, probes that are sent into orbit around some solar system body. The purpose here would be oftentimes we want to map the surface of the planet or the cloud cover of the planet, and we want to get a more comprehensive mapping of it. When we talked about orbits around the Earth, we mentioned that if you send a satellite, say, on a polar orbit, you could eventually map out the entire planet as it spins. And the same tactic can take place here with an orbiter mission around another planet. This will allow you to do some remote sensing, but not as much extensively as if you landed, but it allows you to make some repeat observations over time and not just fly right past and on to the next thing. So an example of an orbiter mission was the Messenger, which was ultimately sent into orbit around Mercury and gave us these nice close-up images of Mercury's surface. As you're seeing here, it basically mapped out the entire surface, giving us a lot of details. There's a lot of different features on Mercury that scientists were interested to understand better. Okay, and finally, we can talk about lander missions. These are probes that actually, of course, land on the surface of a solar system body, and from there, they're going to send back information about the composition, the surface features, other kinds of data, and take really close-up images. This is as good as you can get without sending people. So an example of this was the Mars Curiosity rover sent in 2011, whose goals were to try and look into whether or not there's any signs of biology taking place there on Mars, either in the past or present, geological and chemical processes, planetary processes, and the surface radiation levels. So the Curiosity rover was launched in November of 2011, and it arrived in August of 2012. So it took basically all that time, and you can see some of the different types of trajectories that we talked about to get the Hohmann trajectory to get into that kind of orbit where Mars was located, and actually get to the place that it was targeting and then land on the surface of Mars. This is a look at what the Mars rover, the Curiosity rover, was equipped with. You can see it's got UV sensors, cameras, different chemical little experiments that it could perform, and so on. And it was able to send back really detailed images like the one you're seeing here, and also some chemical information and radiation information on the surface, about the surface. As well as, like I said, these stunning very detailed images from the surface of Mars. And from that, we can learn a lot. Okay, so we've talked about telescopes both on the ground and in space. We've talked about flybys, orbiters, and landers. In addition to that, there are other modes of space exploration that we could discuss. We're not going to really go into them, but there are probes that go through the atmosphere, atmospheric probes, impactor probes, probes that are meant to return samples. And of course, there's the idea of humans exploring other planets. So far, humans have been constrained to performing experiments on the International Space Station since the Apollo days. And so far, humans have not set foot on other planets, only on the moon. So that's something we will discuss more when we talk about, sort of the more futuristic space exploration ideas in the next chapter about space colonization. So I hope you enjoyed this, and I will talk to you again soon. Thanks.